in Haskell, when we do some type level programming, which occasionally we all love to do, we sometimes... Sorry?
Some more than others.
Some more than others, yeah. We sometimes have to resort to some tricks, I would almost say, because Haskell is not a true dependently typed language, at least not yet. And so sometimes when you're working with GADTs, everything is fine, but other times you notice that you run into trouble because you cannot quite express what you want, at least if you're not familiar with the concept of singletons. So today we're going to look at a number of simple functions involving GADTs. We're going to see what exactly is it, whether you need to use these mysterious singletons or not, what they are, and how you can define them and use them.
Yeah, welcome to the Haskell Unfolder, a YouTube series where we discuss all things Haskell. This is episode number 50, so a bit of a milestone. Long may it last. There's many more to come, I hope. As always, we are live streaming this, so if you're online right now, then feel free to submit questions or comments in the chat, and we will try to show them on screen and discuss them.
Yeah, very good. So I'm deliberately going to use what is considered, I guess, the hello world example of programming on the type level or with GADTs, namely length indexed lists or vectors. The reason for that is because, I want to have time to focus on actually explaining about singletons, so I'm not using a more complicated example today. So the idea is indeed that we want to define a data type that is just like lists, but the length of the list should be tracked at the type level. And the way this is usually done is that you define a data type of natural numbers like this. It's an inductive data type of natural numbers, where you say 0 is a natural number and successor takes a natural number and produces a natural number. This is a normal data type, but written in GADT syntax, just for similarity with the rest. But one of the features of Haskell is that if you write a data type, you can then define terms of that data type, as I guess everybody knows. You can define 1 to be the successor of 0, which is a natural number. But you can also promote it, or GHC can promote it for you automatically, so that nat becomes a kind and 0 becomes a type of kind nat, and successor becomes a type constructor that takes a type of kind nat and produces another type of kind nat. And as you see this being done here with these type synonyms that I've written. So here I'm using successor of 0 as a type, and I'm defining a new type called 1, like a type synonym 1, which is defined to be successor of 0. And all these type synonyms here, 1 up to 5, have kind nat. And actually, this used to be the case until not so long ago, but I think since GHC 9.6, you can also enable another language extension, which is called type data. And then you can say type data nat, and then you're immediately saying that this is you're only interested actually in defining a kind and types, rather than having something which is at both levels and sort of hybrid, right? And so you see now that the definition of 1 suddenly becomes a mistake. But the rest still works. Mm-hmm. And then I'm going to define the vector type. The vector type takes 2 type parameters now, but the first one I've given a kind signature. These standalone kind signatures, they're also not in GHC for that long. I forgot the version number when they were introduced.
Yeah, I'm not sure either.
The first argument of vec is of kind nat. The second argument of vec is of kind type. So that's the what was in the old days called star. That's the normal kind that user-defined types such as, but also predefined types such as int, boolean, whatnot have. And if applied to the 2 arguments, you get a type again. And vector has 2 constructors corresponding to the 2 list constructors nil and cons. Nil produces a vector of length 0, cons takes an element and a vector of length n, and then produces a vector of length successor of n. And then I'm saying that I want to be able to use the cons infix with right associativity as we're used also from the list cons operator, and that we want to be able to show vectors. Okay. And
So
with these definitions, yes, sorry.
So far so good.
Yeah, okay, very good. With these definitions, we can then define functions on vectors. So for example, we can define something like vzipwidth, which takes a function from A to B to C, and a vector NA, and a vector of the same length B, and we can then guarantee that the resulting vector is also of the same length, right? We know that the two input vectors must have the same length, and the final vector will have that same length yet again. So we get this function, and we only need to consider the case where both vectors are nil, because then they have the same length, and then the result is nil, or both vectors are conses. And then the definition is not surprising, I think. It's just like what we would do for normal lists. Vzipwidth f of x as y, yes. And yeah, I don't need to actually introduce a name for the f. And I don't need to consider the other two cases, right? They couldn't be reached anyway. They couldn't, like, the vzipwidth cannot actually be called with two vectors of different lengths. So you can never have a nil or a cons and a nil. And there's no warning being generated about the patterns not being exhaustive, and it's all fine, right? Just these two cases needed, nothing else. So that's very good and very straightforward. But if we want to define a different function on vectors, say replicate, what does replicate do on lists? Replicate takes an integer and a value, and then produces a list of A's. And the idea is that if we call replicate n of some x, then we get n copies of that x as a list, right? And we want the same thing as a vector. So we would like to write something like in this case, okay, the lengths are specified as natural numbers. That's sane. So we want to give a natural number. And then we want to take an A, and then we want to generate a vec NA. But even just looking at the type signature, this is weird, right? Because this n here lives at the type level, and it's named, right? And it should be exactly this number. But this relation is currently not clear, right? And if we actually try to define the function like this, if we try to define 0, something is nil, successor n of x is x cons vec nx. Sorry, not vec nx. We replicate nx. I'm getting errors because, I mean, well, actually, my nut now that I declared as a type nut is only living at the type level. But even if I hadn't said that, then I would get a type error in the result, because, right, I mean, I've promised now, if you look at the type signature, that for any natural number and any argument a, I can produce a vector of an arbitrary length. So really this connection between this number and this is not at all clear, right? So there are two problems here. First of all, our nut is living on the term level, not on the type level, right? Secondly, there is no connection between this nut and that nut. So what we would really like is we would somehow want to express that this connection is there by sort of being able to give a name which we can then use, right? And secondly, we would want to somehow state that this nut here should actually be the kind nut and not type nut, and this n should be a type. And there is something planned for GHC to allow this. So there is actually a syntax that you can use which looks like this, which gives you an error message, which I think is saying something like, illegal visible dependent quantification and the type of a term, GHC does not yet support this. And I mean, there is this whole roadmap for dependent Haskell, and there are people working on this for quite some time already, and there's great work still being done. And perhaps at some point we'll be able to write just this. But right now we cannot, right? But what we really want to do here is we want to take the length of the vector as an input, just like we would do for replicate on lists, and we want to do a pattern match on that length, and depending on that length we want to do the one thing or the other thing, and that is something that we cannot easily do, right? And that's why we are in trouble here. I mean, the difference between vzipwidth and vreplicate is that somehow in vzipwidth we can pretend that we're not really pattern matching on the length of the vector, we can just pattern match on one of the input vectors directly. But now we don't have an input vector, so that's not an option, okay? But if we think a little bit, what does Haskell offer? There is a language construct that we are all often using in order to make distinctions on the type level, depending on the choice of a type, right? Do one behavior for one type, do another behavior for another type. And that concept is type classes. So perhaps we can just solve our problem by defining a type class. So let's try that first, because it's in my opinion, a very straightforward solution. We just define a type class replicate. And that type class is indexed by a natural number now as well. So again, I can make that explicit by adding a kind signature saying replicate is a type class which takes a natural number to a constraint in this case. The constraint is the kind of type classes. The kind signature is optional, right? I mean, it's just there for making it clearer that the n here is really something of kind nat. And now I'm just defining replicate, and let me call that replicate C, because we're going to define many different versions, and I want to all be able to tell them apart. So let's call it vreplicate C actually. In this type class, and give it the type A to vec NA. And now let me actually emphasize, because that's always a little bit hidden when you use the class system, that the type signature of vreplicate C, right, is then not just A to vec NA, but it gets this replicate N class constraint. So it's not exactly the same thing as we would want to write here. It's also not exactly the same thing as we did with vzipwidth, where we didn't have any class constraint whatsoever, right? So it's slightly different, and we'll get back to that. But if we accept that for a moment, then we can give an instance for 0, right? And say vreplicate C for 0 does not really need its argument. It will just always return nil. And we can give an instance for replicate successor of n, where vreplicate C of x is x cons. And what do we do now? We simply call vreplicate C on x again. GHC will infer that because we're using cons here, right, and cons like contains a vector which is one element shorter, that we then need a replicate instance for n, right, for like n as a condition. But we can just require that. We can just say what if we have that, and this definition is now accepted, right? And now if you think about it, we have an instance for 0, and we have an instance that goes from n to successor of n. So for every type level natural number, we can actually implement vreplicate, and we can try that out. So let's try that. So one option, like if I just do vreplicate C and would try to evaluate this, I can even try it, gives me an ambiguous type variable, like a lengthy error message from GHC, right? And that's understandable, because right now we don't really know at which type we want to use it, and it's an overloaded type, so like choice of the type matters for the result, obviously. We somehow have to still feed in the number via the context. We can do that via an explicit type signature or via an explicit type argument. So I can just say something like 2 here, because I define 2 as a type synonym up here, right? That's why it's possible. There's nothing really magic about the 2. And then I get a vector of length 2. If I would say 5 here, I would get a vector of length 5. Right?
Yeah, so the at symbol here is critical, right? This is not normal application. This is type application. It's like, I don't know, concat at int or something like this.
Yeah.
Right?
I mean, we could also just do vec char 5, right? I mean, that would
The other way around, isn't it?
5 char, yeah, 5 char. That would work equally well, right? Mm-hmm. I mean, that's another option. And indeed, it is it's useful that we can infer the type, because very often you will use such vectors in contexts where you know the type from somewhere else. So for example, another example is if we call vzipWidth and we already have another vector, let's say a vector that I'm just writing here, which is 1, 2, 3, nil. And then we zip that with vreplicate c of x. And of course, I need to also pass a function that's vzipWidth, not vzip. So, but let's just tuple on these. And now I've not given a type annotation at all, but it's the type of this vector, which is enough for GHC to infer, right? I mean, this is a vector of length 3, and therefore the other vector also has to have length 3. And without explicitly feeding that information to the call to vreplicate, we get the right behavior.
So before you move on, there's a question here that I think we could just quickly clarify. So the question is, and there was a typo in the question, so I'll just rephrase it here rather than show it. The question is, does this still work if we have declared not to be type data? And I mean,
yes, sorry, I removed that in between. I forgot again why. But yes, I mean, I'm not now. Oh yeah, I removed it in between because of our attempt here of defining vreplicate, and I didn't want to let that fail purely because we couldn't use nut on the value level. But I've commented that out for now, and in the development now, we're only using nut as a kind, and the constructors of nut as types.
So specifically, the question talks about the type class and the type application. Now, the type class is indexed by a type, right? And the type application wants a type. So we only need it at the type level. Right? So by having type data there, it says we don't have it at the term level, but we're not using it at the term level. So that's fine.
Yeah. Okay. Yeah. Good question. So could we just stop here? I mean, we haven't even talked about singletons yet, and we seem to have a solution. And indeed, it is a solution, I think. It's just not an ideal solution under all circumstances. And why not? Because that's because of the type signature, right? If you look at the type signature, it has this class constraint. And it doesn't just have any random class constraint. It has a class constraint, which is effectively a class that we defined for the specific function that we wanted to use. And that now means that in principle, if you start using vreplicate somewhere in your code, then this constraint bubbles up to some point. If we call vreplicate on a concrete natural number, that constraint perhaps can be discharged. But in principle, other functions that are quantified over the n will inherit this replicate constraint. And that's bad because it leaks an implementation detail in our code. Right? We might start defining other functions that are also working in a similar way, that are also working indexed over a natural number. We do need to do this kind of type level pattern match. So we define other type classes for those functions, and then we get more and more class constraints, and they're all implementation details. Or perhaps even worse, we write some code in terms of replicate, and then we later decide we want to replace replicate by a different function, which depends on a different class. And then suddenly all our type signatures change when they really shouldn't, because it is just something that we do with natural numbers, and we shouldn't necessarily have to say what we're doing with natural numbers. So that is a little bit problematic, right? But nevertheless, it's a sort of one good ingredient of the solution. Now, for a different approach, let's consider why does vzipWidth work, right? Why is that one okay? And even though we're also kind of making a distinction, right? I mean, it works differently for vectors of length 0, if you like, than for vectors of length successor of n. But that is because we pattern match on the vector GADT, and because the constructors of the vector GADT are helping us to determine what the length of the vector is, we can kind of bridge between the term and the value level by matching on a term, namely the concrete vector. We learn something about the type. Now, in vreplicate, we don't have a vector and we don't want a vector, but perhaps we can take the essence of this idea and like strip vectors of everything that has to do with vectors and just keep this idea of using the terms to like learn something about the types. And that's what gets us to singletons. So I can actually define the singleton right up here underneath snat. Underneath nat, and I'm calling it snat for singleton on nat. And like vectors, it's a type that is indexed over natural numbers. But unlike vectors, we no longer carry any element around because we're not interested in elements, right? We're only interested in the natural numbers. And we want something that corresponds to nil or 0. So we give it a constructor S0. And that one gives us an snat of 0. And we want something that corresponds to cons or successor. But again, we're not really caring about the elements at all. We only care about the natural number structure, so to speak. So we let a successor to take an snat of n to an snat of successor of n. So really, if you compare nat and snat, they look very, very similar, right? I mean, both have the same number of constructors. The constructors have the same name. The constructors have the same number of arguments. But there is this one-to-one correspondence, right? S0 is just set up so that it produces an snat of 0. And S successor is set up so that it produces an snat of successor of something, and then takes a singleton, like an snat of that n as an argument. And so this one-to-one correspondence between types of kind nat and terms of type snat is why types such as snat are called singleton types, right? And because there is this one-to-one correspondence, we can use them to fix our problem, because we can pattern match on an snat. It contains exactly as much information as a natural number, right? Has the same constructors and so on. But by pattern matching on this term, we also learn something about this type argument, which we can then use in order to know what the like the actual type of the result must be. And so we can see this in action. And this one, I mean, to go back to the question that has just been asked, this needs to be on the term level, right? I mean, this one we want on the type level, but this one we absolutely want on the term level. That's the whole point, right? So let's define a version of replicate based on singletons. And perhaps I should briefly split the screen so that I have the definition of snat still visible. So snat n a to vec na. So we do S0, that gives us nil. S successor of n, x. This gives us x cons. We replicate S nx. That's it, right? So this is actually very close to this definition that we wanted to write, right, originally. If I copy that down here, and now I can also close the other window again. If we compare these two cases, they're looking relatively similar now, right? I mean, this snat n you can see as an encoding for this dependent quantification, if you like, and then this S0 and S successor of n you can see as an encoding for the fact that we actually want to pattern match on the type, right? So this is really, it's an encoding, but it is relatively straightforward. Now, the problem with this version, even though it works, is that we always have to give the type argument, right? So if we want to call vreplicate s on 2, right? I don't even have a types like a synonym. A type synonym wouldn't be right anyway, but I actually have to write s suck of s0 of x, and then I can evaluate that. But writing an argument like this explicitly is tedious, right? And like if I wanted to use vreplicate on the right-hand side of a vzipwidth, I still would have to provide that singleton argument. There is only really one possible correct value to put there, but I have to write it. So that's annoying, right? So the idea now is perhaps we can combine the two things, right? The class is good because it's implicit, but this was a specific class for a specific function. But now we have a generic concept, this singleton nut. And if we define a class that produces the singleton nut, then we are much better off, because like all of a sudden we still need class constraint, but they no longer really leak implementation details. Instead, they simply say that we perform a type level pattern match on natural numbers, which is a much more generic thing to say. Okay, so how do we do that? We can do define a class snat I. I usually use this naming scheme. I think it was similarly used by Richard Eisenberg, who originally wrote a lot about singletons, and also introduced the singletons library, by the way, which defines a couple of these things, including helper functions. But the concept of singletons is very general. You don't need the singletons library. You can use it, but you don't have to. Other libraries, packages on Hackage do their own things. They often use slightly different terminology. By the way, GHC also has some built-in, like in base, type level things. It has type level natural numbers, but they are not really inductive. It has type level strings and so on, but it also uses singletons for those. So there is an snut type in base, which is different from ours. And there is an S symbol, I think, for singleton non-symbols. And the implicit variants are called known nut and known symbol in GHC. So that would be another possible terminology. But I'm just using snut I. Yeah, thank you. I'm just using this one here, and I'm just having one method which allows us to compute the actual snut of n. And the instances are very straightforward. One for 0 again, which is S0, and one which goes from snut I n to snut I successor of n again, which says, well, if we do an S successor, and then we compute using the same class the snut for the predecessor. Okay, this just is accepted. And with this, I can now define a version vreplicate si, which takes an snut I n and gives us an a to vec n si. And I can just write it in this case as a wrapper around the vreplicate s that we already have, where I infer the snut from the context. And now the use of vreplicate si is basically the same as the use of the vreplicate c that we had up here. So if I copy these examples down here, delete the results for now so that we're clear that I'm not just overlooking something, replace the calls to replicate C with vreplicate si, and then evaluate, then here we get our results as expected as well. Mm-hmm. Okay, so that's basically the story on singletons, and the same story also applies for like basically type level in pattern matching on other data types, right? If you had a Boolean and you had a type level Boolean, you can very easily define a singleton for a type level Boolean. If you have a type level list or something like that, you can define a singleton for a type level list. It's slightly more complicated for lists if you want them to be polymorphic, because you have to think about what to do with the arguments. But in principle, this general idea just generalizes to arbitrary data types that are lifted to the type level, so that there's nothing about this.
There's two questions that we can take them at the end, or you can take them now.
First.
Yeah. Okay.
No, let's take them now.
Okay. So the first question is, so this is about the start of what you were talking about, like NAT. Like you introduced this type, like we lifted NAT to the type level, right? And then we said this is a new kind NAT. And so this person asks, is something of the kind NAT also of kind type?
Yeah, okay, so this is actually a surprisingly tricky question, but in Haskell, the answer is relatively simple. So if you ask for the kind of NAT, right, you get that, okay, now I haven't enabled sort of the right extension so that star is disabled. So, but you basically, star is the same as type. You get that NAT itself is of kind type. So everything, like from the type level on, basically everything in GHC is considered more or less the same these days. I mean, already for quite some time. So types and kinds, there is not really a deep distinction. So you can always ask for the kind of a type, or also for the kind of a kind. And in the end, it's always going to be type, right? I mean, like it's always going to be type. There is some logical problems with that if you're doing that. And this viewpoint that NAT is a subset of type, I would like try to get away from. It's really, it's like see it as a different thing. Really what this should be sort of like a different type. This is what other systems are doing, sort of a higher sort of types, something like that. And then type is one thing of this higher sort of types, and NAT is another thing of this higher sort of types, or let's call it kind or whatever, right? But just use a different identifier to get that idea right. So basically, I don't think the subset view is correct, but technically, it is true that if you ask for the kind of anything that you're defining, then if you ask often enough, you always get type, right? And that's
so
there was another question.
Yeah, there's a few actually. Just to make sure that I mean, I understood this question slightly differently, and I don't know if your interpretation was correct or mine.
Okay, perhaps I just completely misunderstood the question. If something of kind not also of kind type. Oh yeah, perhaps I really just misunderstood the question. Sorry for that. No, then the answer is just no.
Right. That's yes.
So no, NAT and type are completely different kinds, and 0 is not of kind type.
Right? Yeah. So in particular, if you have a function that says like for all a something of type, for all a of kind type, you cannot pass 0.
Yeah.
And even if
or also, I mean, if I would no, I mean, actually what you said is probably a good example. Yeah. So if we simply say if we try to call the identity function at the kind 0 or at the type 0, sorry, right? Then this is just giving us a kind error.
Kind error,
right? Even if we're not even giving a real argument yet, but even this term here, even if we just ask for the type of it, you get the same error. That's already wrong. Whereas if we would call it as something which actually has the kind type, then it's just fine. No, sorry for misunderstanding.
No, yeah. So this next one is not really a question so much as a comment, but it's nonetheless, I mean, I think for some people this might be useful. So SNAT is equivalent to vec in the same way that NAT is equivalent to list.
Yeah.
So yeah, I mean, for me personally, I found this So this kind of description more difficult than singletons? Like once I understood singletons, I understood this better rather than the other way around. But maybe for some of the people, this is
no, but I
is a
mean
useful thing to
that's
think about.
certainly true. Yeah,
Yeah.
I think it's a good analogy. Yeah.
So Vincent asks, apart from the ability to write for all n of type that we showed, what is missing and waiting for independent Haskell? How long do you have?
I don't think we have time to really go deeply into that. And also, I'm not the expert. I think these days, Vlad is. I mean, int index is his. I think he's doing most of the work, and some other people are also. There are some things that are working with dependent quantification, but they are mostly involving dependent quantification one level up. So if you want to actually express a dependent quantification or purely on the type level, not something in a function type signature. And what we have here, if we wanted something like our wishful vreplicate to work, it's actually, yeah, I mean, you need some kind of replacement for this. Yeah? I mean, you need to kind of translate this into something which is similar to what you also would either translate vreplicate C into or vreplicate S into. And so basically you need something like a singleton construction behind the scenes anyway, but you wouldn't necessarily force the user to write it or worry about it. It would just be something which the compiler does internally. But it's not at all easy, I think. It like crosscuts with a lot of assumptions that GHC makes in particular ways, which have to be adapted and changed. And it's I think very delicate fine-tuning that needs to be done in the compiler. I don't think it's theoretically difficult, right? I mean, there are other languages that do it, but like especially because GHC or Haskell is an existing language with a large ecosystem and many running programs, and you don't want to break anything, it's actually very, very hard to do it. Yeah.
So there's a question which is basically now asked in 3 different ways. So let me show you just one of them.
There's actually more that I wanted to show, but I mean, I can I can answer questions. I'm very
I know, but I think we're
question.
basically
so I'm very
Would you be able to give a quick example of using vec NA in a context where n is unknown at compile time?
So
I mean, show for example.
I think what you probably consider cheating is if I just say vzipwith already uses vec NA in a context where we don't know a concrete n, right? Because
no, that's not what he means, right?
So I think I have to speculate what you mean, but I think
read from a file.
What you probably mean, yeah. So okay, what you probably mean is you have something of which you don't know what it is, right? But you want to establish something like at a boundary. Yeah, you read something from a file, or you have a normal list, or something like that, right? Yeah. And so for example, what you could imagine is like, say, you might want to write something like test lists, and you're giving it 2 lists. And I mean, it's all a little bit contrived now, right? But you want to basically check whether they're both the same length. And if they're the same length, you can basically supply a continuation that gets 2 vectors of the same length and produces some result. And you can quantify that over n. Otherwise, you just produce a default value, and then you can always go to that default value. Something like this. This would be.
So just to be clear, I mean, yes, I think this is a nice example. So the for all n in here is nested, and that's necessary, right? Like the caller does not know what n is, therefore the caller must be told what n is. That's why the for all is nested.
Yeah. Right. Okay, so if we want to, I mean, so this is like, right, this is basically like testing two lists, whether they have the same length, right? And if they have the same length, you can apply this function, like you can supply a continuation to this function, which can treat the two lists as vectors. And then we don't know the length of the vectors, but we still know that the length of the two vectors is the same. So we could, for example, call our vzipwidth on it. And if not, we have to say something else, because it's obviously something that can fail now. And this is always, this is typical, right? If you write some parsing function, some validation function, some function that establishes a boundary between a less trusted world and a more trusted world, there's always the potential for failure. And at that point, the failure is to be expected. But the good thing is that if you're then producing a witness of the successful outcome of your test, which in this case we kind of do by saying, oh yeah, if we check that the two lengths of the lists are actually the same, we turn them into vectors, then you don't have to worry about it again. All right, the moment you then work with these vectors, you really know they have the same length, and you no longer have to do additional runtime checks every time you call some functions that assume that. And that's why this this boundary is useful, right? And I mean, okay, I can try to write it. I didn't prepare this. So if we have two empty lists, right, and we have our success continuation and our failure continuation, then in this case we want to call the success continuation with nil and nil. So that's simple. And if we have two non-empty lists, that's probably the most complicated case. Worry about that at the end. And in this case, I need to consider the other cases, right? That I have one empty and one non-empty list. But that's simple, because in that case, I just call my failure continuation. Okay. So now, what do I do here? Well, so basically, I have to test the lists XS and YS, and I don't have to change my failure continuation, but I do have to change my success continuation, because previously, what I'm getting is something which can deal with, let me see, what K success is like expecting two vectors of length successor of n, so to speak. But the success continuation I have to pass to test lists is only getting two vectors of length n, right? So this is getting sort of a VXS version and a VYS version in the case that XS and YS have actually the same length. So basically vector versions of these two lists. And in order to build the thing that I can call K success with, I have to now call vector cons on this one and vector cons on that one. VYS. Okay, and I think that's it, right? And I mean, this is just key K fail with an underscore. So this is a little bit perhaps a cryptic way of writing it. I wanted to avoid also having to introduce an existential wrapper. I mean, like something like this can also be done using an existentially quantified type, where you wrap the two vectors up in something which hides the n, and that is perhaps like equally idiomatic than this continuation passing. But both works, right? And I mean, but this sort of stuff is common, and it's just one example of a thing that you can do. And I hope that answers the question.
I think, yeah, for sure. And I think this is rather cool, right? So basically, we're doing a check that these two things are equal. But it's not just like this goes back to an episode that we did a long time ago on Boolean blindness and evidence, right?
Yeah.
Here we're doing a check if two lists are the same, and if they are, we're not just giving you a bool, true or false. We're giving you a proof, a type level proof. I mean, up to a point, right? But we give you type level evidence at least that these two things
Yeah.
really are the same.
Yeah. I mean, one of the things is that we might, I mean, if we now actually want to, I mean, no, actually, I think it's fine. I mean, let's just try it out. I mean, let's like just to make it complete. Let's actually see if we can call test lists on 1, 2, 3 and 4, 5, 6. And then what we want is we want to call vzip with pair, so to speak. And otherwise, we just return an empty list. vzip with is returning a vector. Oh, this is actually probably problematic because, I mean, the way I've now defined it, I have to always return something which cannot depend on the n. You can work around that as well, but we would need another toList function in the end again, right? I mean, it's a very common thing, though, that you like basically you have a trusted kernel. You're doing something with the trustworthy stuff in the very end. You're going to something less trustworthy anyway, but. Yeah, can I just do that very, very quickly as well? So just that I can show that the whole thing works. Like to list of A to list. Derive foldable, yeah. Probably would be easier. But it's already almost written. So let's do
You're faster than the compiler.
vxs, vys, to list, vxs. It's a very complicated way to write a zip with on lists, but what's going on? No.
You need to do failure continuation.
The failure continuation was supposed to be an empty list. Yeah, okay. Yeah, it is a very complicated way to write a zip with on lists, but it is hopefully nevertheless demonstrating this feature, right? And
typically this boundary is complicated, but now this looks very complicated because with the boundary, the thing that we do inside the boundary is tiny, right? Typically, you'd have the boundary at the outer levels, and everything inside is a big thing, and then at the very end, you go back again to something inside.
Okay. I don't want to do the thing that I originally wanted to do, but I perhaps want to briefly at least point out what I would still have talked about. And one of the things that is observable if you look a little bit is that, like I have said, we replicate C, the class-based version, and we replicate SI, the implicit singleton-based version, can be used in exactly the same way. But they don't actually have exactly the same runtime behavior in the sense that vreplicate C is class-based, and class resolution in Haskell happens mostly at compile time. And that means that if you look at the core code that is generated for a concrete call to vreplicate C, like say vreplicate C type level 5 on X, you get a compile time unfolded vector of length 5. Whereas for vreplicate SI, you get nothing. You get a function that computes based on the runtime singleton because it's a recursive function operating on a runtime value. And that's not necessarily saying which is better. It's just saying that it's different. And you could ask the question, like, can you do sort of a single class-based version of a singleton-like thing as well that is evaluated at compile time? And the answer to that is, in essence, yes, if you add something like an induction principle or an elimination principle for natural numbers to the class and use that instead. But I think it leads too far for today's episode. It's also not necessary typically. Most of the time, you're just going to be okay with these like value level singletons anyway. I mean, type level programming is not necessarily massively efficient in Haskell. That's not typically the reason why you're using it. There are some cases where it can actually help efficiency as well, but the general aspect is mostly you want to prevent errors. You want to make things correct by construction. You want to rule out impossible states and so on and so forth. And if you're using it for something where sort of the runtime doesn't massively matter, then these singletons won't massively matter either. Okay. Any more questions, or shall we leave it there?
Let's leave it there.
Okay. It was a long episode. Thank you for everyone who had the patience to stay until the end, and hopefully see you again soon. Let me.
Yeah, thanks everyone. It was great to have so many questions. Changed the episode ever so slightly, but that's good. I mean, we always emphasize we like interactivity, so thanks everyone for that. If you enjoyed it, please like and subscribe. Feel free to leave any comments below. We'll leave the chat open for a few more minutes if you have any more questions. And otherwise, feel free to pop them down below in the comments, and we'll always try to address them there. And hope to see everyone again very soon.
Oh, thank you.